and you have more adults to help you out. This is great.
Seems like
All
we are
right.
ready, right?
Ok, está bien. Pues ven, yo hago la presentación en español al instituto. Nuevamente, estimados personas del instituto, investigadores, técnicos, funcionarios, pues también es un placer nuevamente tenerlos como cada 8 días en el coloquio, ¿sí? Es un placer que estemos conectados. El hecho de que nos veamos las caras, pues eso nos da alegría, ¿sí? Ver que estamos bien. Hoy tenemos la oportunidad de tener a Jessie Christiansen, ¿sí? Es una invitada de Gilén. Gilén ha trabajado con ella, entonces Gilén la va a presentar. Adelante, Gilén.
Gracias, Nisim. So I will read. Yes, I will read the introduction in English. Dr. Jessie Christiansen does research primarily in exoplanet systems, including exoplanet catalogs, occurrence rate, light curve software, and exoplanet atmospheres, and also studies variable stars. Dr. Christiansen got a Bachelor of Science from Griffith University in Brisbane, Australia, and a Bachelor of Science honors from the Australian National University in Canberra, in Australia. Dr. Christiansen got a PhD in astronomy from the University of South Wales in Sydney. She was then a postdoctoral research fellow at the Harvard Smithsonian Center for Astrophysics, and then later a staff scientist in the Kepler Science Office and NASA Ames Research Center and the SETI Institute, and then later a staff scientist at the NASA Exoplanet Science Institute and Caltech. Dr. Jessie Christiansen is a deputy science lead at the NASA Exoplanet Archive, a research scientist at the NASA Exoplanet Science Institute at Griffith University, outstanding young alumnus from 2018, and the mother of twin tornadoes. Welcome, Jessie, and I look forward to hear about the exoplanet demographics.
Thank you so much, and it's a real pleasure to be here today with you to talk about exoplanet demographics. Thank you again for the invitation. So today I want to talk about building this bigger picture of exoplanet demographics. We've so far concentrated on very small areas of parameter space in exoplanets, each survey dedicated to its own space. And I'm going to talk about some of those surveys. But today I really want to step back and think about the larger picture. How do we piece all of these together to create this overall picture of the population of planets in our galaxy? First, I wanted to start with an overview of what IPAC is, because that's the institute that I work at, and most people aren't familiar with it. So IPAC is at Caltech, the California Institute of Technology, and it's a NASA-style science center. So we're run by Caltech, but we administer many NASA projects. So we're a data center for many projects and an archive for projects that have ended, including the great observatories, including Spitzer, for instance. We administer NASA, NSF, and privately funded projects. We have a large outreach staff who work on incredible videos and visualizations and podcasts to reach the public. And it's normally, when it's not 2020, a really vibrant research environment and a great place to work. So what do we have? We have the Spitzer Science Center before Spitzer turned off earlier this year. The NEXI, which is where I work, the NASA Exoplanet Science Institute. We host the NASA Extragalactic Database, NED. The galactic astronomers and extragalactic astronomers among you are probably familiar with NED. We host URSA, the Infrared Science Archive. We also help archive data from NEOWISE, the Zwicky Transient Facility at Palomar, and other projects. And then we're also helping to support development of future projects. So the Euclid mission, WFIRST, which has now been renamed to the Roman telescope. We're involved in that, in the imaging instrument. The Near Earth Orbiter Surveyor, and ESA's aerial mission. NASA's contributing an instrument called CASE to that, and IPAC is part of that effort. So that's just a 2-minute primer on what IPAC is, so you have a better idea of where I work, because it's not in a university department, it's at this research institute. Okay, so let's get back to planets. This is what the view of the overall picture of planets looked like before 2010. So on this axis, I'm showing the orbital period of the planet in days. And on this axis, I'm showing the size relative to Earth. So if you go to 1 Earth radius and 365 days, here's the Earth. And in fact, these 4 squares are the inner solar system planets, Mercury, Venus, Earth, and Mars. So you can see that before 2010, the exoplanets that we had found looked nothing like the exoplanets in our solar system. The majority of them were very short period, down here at just a few days, and very hot because they were at such short periods, and very large. So 11 times the size of Earth is the radius of Jupiter. So these are all hot Jupiters. These are all gas giant planets orbiting very close. And we were starting to kind of edge into these other parts of parameter space. Now in 2020, the picture looks more like this. And you can see we've really filled out this space between the hot Jupiters, which again, nothing like the planets in our solar system, and the planets in our solar system. We've really started filling this out. What we can do with these thousands of planet discoveries, we have over 4,000 now, is start asking some more interesting questions. These include, what's the true underlying population of planets that we would have to assume is there in order to create this set of observations? There's a whole bunch of observational biases going on here. How do we correct for those to say this is what's truly happening underneath? Sorry, there we go. How do planet occurrence rates change with different kinds of stars? Are some kinds of stars better at making planets or worse at making planets? Better at making certain types of planets in certain types of configurations? We can start to ask that. Asking those questions allows us to then move on to what's the physics happening? What are the processes that are governing planet formation and migration and evolution? What are the dominant physical processes that sculpt the planets that we see today? Basically, where does this population come from? What's driving it? And it's really exciting that we're finally in the exoplanet field moving from stamp collecting, like this is the biggest and this is the smallest and this is the hottest, to what's the physics underneath. That's, for me, the really exciting part. So just an overview of the talk. First, I'm going to talk about the NASA Kepler mission and where we're at with the analysis of those data. Then I'm going to move on to K2, which was the sequel to the Kepler mission. And the group that I lead at IPAC is working on this mission, the data from this mission. I'll move on to TESS, which is NASA's current latest and greatest exoplanet hunter, and what the opportunities are there. And finally, I'll take this step back and say, how do we start putting this together? So the Kepler mission was a spacecraft that launched in 2009. It's a 1-meter optical telescope. So this spacecraft bus here is about the size of a van, like a school van. It uses the transit method to discover planets. So I'm showing here on the right just a video of how the transit method works. So basically, if you have your planetary system lined up just right, the planets will pass in front of the star and block some of the light. Now, of course, we don't see this top part. We see this bottom part. We're just measuring the brightness of the light over and over again, and then these dips happen. And if you get enough data, this is 500 hours of Spitzer data on the TRAPPIST-1 system, you start to see the same dips happening over and over again. And you can say, okay, there's a planet there that's orbiting around the star. TRAPPIST-1 has 7 planets, so there's lots of dips. And this is what we do. We monitor the brightness of stars over and over again, waiting for dips. The science goal of the Kepler mission was to measure eta-Earth, which is the frequency of Earth-sized planets in the habitable zones of stars like the sun. 3 criteria to be Earth-like. That's eta-Earth. That's what we were trying to do. How common is the Earth? Is the Earth common or rare? Are there many Earths in the galaxy, or are there very few? And to do that, we monitored one patch of sky in the constellation Cygnus for 4 years and just observed the same 200,000 stars over and over and over again. The actual observations are very boring. So how do we get an occurrence rate? How do we turn this mass of detections into an occurrence rate? I think this is the only slide with equations, so we can do it. We can get through this. So to measure eta-Earth, you need 2 things. You need the number of real Earth-like planets in your sample. So Kepler made a bunch of detections, but some of those were false positives. They were signals in the data caused by something that wasn't a planet, which includes astrophysical false positives and instrumental false positives. So if the spacecraft just burped and a little dip appeared in the light curve, that actually happens more often than you might think. They actually pollute your sample of planets with false positives. And this is basically understanding the reliability of your sample. How reliable is your set of planet candidates that you found? How much can you trust that they're all planets? The number of real planets, and then you need to know the number of stars around which you could have detected an Earth-like planet. So that is a function of two things, and that's this bottom equation. There's two reasons why you might not be able to be detected. One is, as I mentioned, the transit method relies on your planetary system being lined up just right. Most planets don't transit. And that's this geometric probability here. There's a probability that a given system will transit. It depends on basically the distance of the planet from the star and the size of the star. It tells you the probability, just mathematically, if everything is randomly distributed on the sky, that it'll be lined up just right. And then there's the probability for a given signal to noise of your signal that your pipeline, your algorithm will actually detect it. So you need to sum over all of these probabilities to get the total number of stars around which you would have been able to see an Earth-like planet. So that's pretty straightforward. If you find 10 Earth-like planets and there were 100 stars around which you could have found Earth-like planets, your eta Earth is 10%. Those two numbers, once you get those two numbers, the math is actually easy. It's getting those two numbers. That's the trick. So you need three ingredients to get those two numbers. One is a stellar population where you understand the stellar parameters well and uniformly. You've uniformly generated the parameters for the whole stellar parameter set. So there's no biases, there's no weird step functions where you've brought in another catalog which had some calibration offset. You just want one set of uniform parameters. You also need a uniformly produced planet candidate catalog. Now, when Kepler started, we were all looking at the signals by eye. There was a group of us who would get together Tuesday mornings and just look at light curves. That's a really fun activity, but a really bad way to do statistics, because how do you quantify how well someone is looking with their eyes and seeing signals? It's really quite difficult. Trust me, I tried. So we needed to come up with an algorithmic way of characterizing these signals, which is what we did. The final thing you need to understand is these two words here, the reliability and the completeness. How many things did you miss that you should have found? How many things did you call planets that aren't planets? And now for the rest of the talk, I'm going to actually do a little bit of a swerve on you. I've defined eta Earth, the frequency of Earth-like planets around stars like the sun in the habitable zone. The problem with eta Earth is everybody has their own definition of what an Earth-sized planet is and how big the habitable zone is and what a sun-like star is. You would think that we could converge, but we have not. So everybody has their own little box that they draw, which is eta Earth. So instead, for comparing different people's calculations, I'm going to introduce this concept of gamma Earth, which is whatever model you fit, however big your space is you defined for eta Earth, I want you to evaluate your model exactly at 1 Earth radius and 365 days. Just tell me in your model how many planets are there. That way we can compare all of these different ways of doing the calculation by saying, just give me the same reference point for everything. So for the rest of the talk, I'll be talking about gamma Earth, just to give you a heads up. Okay, so for Kepler, where are we at? We have this final planet candidate catalog over here, you can see. The little box here is where you'd think Earth-like planets would be. You can see that we didn't find many candidates that are Earth-like, which is unfortunate for a mission that's supposed to do this, but that's another story. We have now completed our calculations of how complete and reliable the Kepler pipeline is. That's been a major part of my work for the past decade, has been defining and measuring the completeness of the Kepler pipeline. And my final paper in the series just came out on arXiv 2 days ago. So that's exciting. Another thing that happened is that Gaia DR2 came out. Gaia DR2 let us finally assess the stars in the Kepler field on roughly equal footing and come up with this uniform stellar parameter set. Now, I show this animation because it's a little bit depressing. Let me explain what it is. Here, when all the points are down in the bottom right-hand corner, these were all of the planet candidates we thought were Earth-like planets in the habitable zones of Sun-like stars before Gaia DR2. Then Gaia DR2 came on, and if you change the parameters of the star that your planet is orbiting, the planet parameters change as well, because everything you measure from a light curve is a relative property. The relative size of the planet to the star is what that depth is telling you. So what happened was that a lot of our stars got bigger and therefore they got hotter. So a lot of these candidates that were originally in the habitable zone and were rocky became too large. They became this is 2 Earth radius here. They got too big to be rocky and they got too hot. This is the insolation relative to Earth. So the number of candidates we had went down by a good fraction. And that was kind of depressing, but it's the scientific truth. So we move forward with what we have. And here's the entire stellar parameter set from Gaia DR2. This is the cleaned up HR diagram. Finally, something that we discovered is that there's an additional completeness correction that you need to make. And this is that if you have more than one planet transiting in the same light curve, the Kepler pipeline has a harder time finding the second and third and fourth planets than it did finding the first. So a lot of the work that I had done assessing how well the pipeline was doing at finding things considered independent individual signals. I didn't consider multiple signals in the same light curve. And it turns out that's an error because multiple signals in the same light curve affect each other's detectability. What that means is that for long period, so these are candidates with periods between 200 and 500 days, there's a significant penalty. This is the detection rate as a function of the signal to noise. MES down here is what we used as our signal to noise measure. And you can see for the first signal in the pipeline, you asymptote up here at like 90%. 90% of the first signals in the light curve are found. For a signal to noise of the same amount, so both of these signals have a signal to noise of 14, you only have a 50% chance of recovering the second or third or fourth signal. So that's a really important correction. That could be quite large since all of our Earth-like planets are out in this period range. So we're probably missing a lot of these because of this correction. Okay, and I wanted to highlight that this is work being done by Jonathan Zink, who's a graduate student at UCLA, who is on the job market this year, and he's a very excellent student, so look out for his applications. Okay, so what does this mean for Gamma Earth? So what I'm showing here are prior to 2015 and earlier, what our estimates for Gamma Earth were like. And the reason I start here is because you can see there's 3 orders of magnitude between the highest possible values and the lowest possible values. This is, 1%, and this is 100%, or 0.1% and 100%. It's very large. So for several years, we did not know what Gamma Earth was. Since those major developments I've mentioned, the pictures actually started to converge somewhat, which is good. You can see we've dropped these several orders of magnitude range, and we're kind of, if this is 10% and this is 100%, we're kind of here, we're kind of between like 10% and 50%. So most of the more recent Gamma Earth calculations have landed here in this 10% to 50% range, which is only half an order of magnitude. The uncertainties at this point are largely due to the fact that, remember that animation I showed? There's not a lot of candidates in the space that you need to constrain A to Earth. So these are actually Poisson uncertainties driven by the small number of planets. So just to show you, even at this point, I've highlighted some of the, recent work. Even the recent work is all doing things differently. Some people are using our reliability, some people aren't. Some people are including the planet multiplicity correction, which is this additional detection efficiency loss that I mentioned. Some people aren't. Most people aren't. This is Michelle Kunamoto. She wrote her very own pipeline and did her whole own separate occurrence rate calculation and actually landed pretty close to some of these other numbers. So that's reassuring. But just to say, we haven't really converged yet on the best way of doing things. So there's still work to be done. Here are some of the things we still have to do. One is to address the issue of stellar multiplicity. We assume that most of the stars in the Kepler field are single. That's not true. We know that lots of stars in the sky are binaries. Now, Gaia has helped us to get down to separations of about 1 arcsecond. So we can basically say, okay, we can resolve any stars where the distance between them is greater than 1 arcsecond. So that helps us clean up a bunch. Kepler has 4 arcsecond pixels. They're actually quite big. So these stars will all get blended together. But the problem is we haven't done high resolution adaptive optics on every star in the field because that would be incredibly expensive. So we have to make assumptions. The problem is, if you assume that all these stars are single, you make 2 mistakes. The first mistake is that any candidates you see around those stars, you will have the parameters wrong. Because as I said, the parameters are all measured relative to the star. So if you have your stellar parameters wrong, then you have your planet parameters wrong. The second, more subtle error that you make is that for the non-host stars, you will measure their detection efficiency wrong if you assume they're singles instead of binaries. What that means is if you thought you had 10,000 stars around which you could have been sensitive to an Earth-sized planet, but 5,000 of those were actually in binaries that you didn't know about, then you were never sensitive to Earth-sized planets around those binaries. The stars would have diluted the transit too much. So your actual number is 5,000 stars that you're sensitive, and then you're going to do your whole calculation wrong because you have your number of stars off by a factor of 2. So this is really important to correct for. We're in the middle of trying to characterize this. What we did was we chose 2,000 stars from the Kepler sample around which we think you could have detected an Earth-sized planet. And we selected 200 of those randomly. You can see their distribution here. They're the colored points on top of the gray points. And we're following those up with the 5-meter Hale telescope at Palomar with adaptive optics to say, are they binaries or not? What's the rate of binarity? The very first one of our 200 stars, when we looked at it, was a triple. And it was like, okay, that's why we're doing this. We've only done about 2/3 of the sample. And the preliminary, 2 sigma result is that the multiplicity seems to be higher for these stars than for the planet hosting stars. But unfortunately, because of COVID, Palomar was closed. We haven't been able to complete our sample yet. We're hoping that we get time next year to actually turn this 2 sigma result either into something more robust or either it goes away. So we need to get the rest of our data set. Another thing I wanted to mention is something we haven't addressed yet is how dangerous it is to extrapolate. Now, you saw from the candidate catalog that I showed earlier, and I'm showing it again here, most of the planets we find are short period. We don't find a lot of planets out here. And that's due to both of those terms. They're much less likely to transit, so we're just going to see fewer of them. And they're typically lower signal to noise. You have fewer transits to add together to create a signal. So you're more likely to miss them in the pipeline. But that means if you're trying to calculate an occurrence rate here in this box, a lot of people fit a power law in period, and they can, it could be a broken power law or a straight power law. But the planets down here at short periods are doing all of the heavy lifting there. They're really constraining the bottom half of that power law, and then the rest of the power law, my arm's going to disappear into my virtual background. The rest of the power law is very weakly constrained by the small number of planets out here. Now, how dangerous is that though? Ilaria Pascucci had a paper last year showing that depending on where you fit your power law, so if you started at 2 days, you would get very high values for gamma Earth, 60%, 80%. But If you started at 12 days, so you eliminated all the planets between 2 and 12 days, that dropped to 15 to 20%. And if you eliminated even more of the short period planets and only started at 25 days, now you're down to below 10% because you've lost all of that power down there at short periods. Now, physically, the underlying reason we believe that this is dangerous is that rocky planets at short periods might not have started as rocky planets. They might have started as Neptune-sized or above volatile-rich or gas-rich planets that were then stripped by their proximity to the star. They're so close to the star that their atmospheres have been stripped away, and now you're seeing this rocky core. What that means is at short periods, you might be seeing two populations of rocky planets. One is primordial Earth-sized rocky planets that were only ever going to be Earth-sized. Those are the ones we really care about. But there's a second population of these stripped cores, which is likely bumping up the number of rocky planets at short period and skewing our power law. So this is something we need to try and address. So moving forward with Kepler, there's some things we can do. We have to finish doing our planet and stellar multiplicity corrections. We'd like to come up with a better way of addressing reliability. I didn't really talk about it, but it's a very basic approach at the moment that could be handled better. Something else I didn't talk about is that we could confirm some of these candidates. Some of the candidates are low reliability. So they look a lot like systematic noise, but they still pass our thresholds. If we could use something like Hubble to follow them up and confirm, that would give us a lot more confidence in our reliability thresholds, that even though these were low reliability, they passed our thresholds, they're real candidates. And finally, as I was just mentioning with the stripped cores, we'd like to improve our population model for these extrapolations to include a two-component fit at short periods, the stripped cores and the primordial Earth-sized things. There's not a lot of good prospects for getting more data to constrain Eta-Earth, unfortunately. Earthfinder is a concept for a space-based radial velocity mission that, if it launched, would be sensitive to Earth-sized planets. The Roman telescope, I'll talk a little bit more about its sensitivity at the end of the talk, but the Roman telescope is a possibility. Earth is kind of at the edge of its detection sensitivity. Plato is a European mission, which is going to launch in a few years, which is kind of like Kepler, and in fact will go back to the Kepler field for some amount of time, possibly allowing us to confirm some of these low reliability planets. But at most, it will look at the Kepler field for a year. So it's not really going to be an independent search for Earth-like planets, which have year-long orbits. Okay, so that's Kepler. That's the current picture of our understanding of Eta-Earth with Kepler. When Kepler broke, when the telescope had its hardware failures in 2013, we thought, oh, well, that's done. But actually, the very clever engineers came up with a solution that allowed us to use the telescope to do an ecliptic plane survey. So the K2 mission, which was Kepler's second life as a spacecraft, ran for 4 years from 2014 to 2018, and it did this survey of the ecliptic plane. So it looked at 19 fields for up to about 80 days in these stairs. It would move every 2 to 3 months around the ecliptic. Now, that's pretty cool for a bunch of reasons. One is that the ecliptic samples high and low galactic latitudes. That's really interesting in terms of the types of stars that you're looking at. And the population, like the galactic structure. Could you start to map out exoplanet demographics as a function of galactic structure? The target list for K2, unlike Kepler, was entirely guest observer driven. So Kepler had this one question: how common are planets around stars like the sun? So most of the stars that Kepler looked at were sun-like stars. K2 didn't have that restriction. So K2 looked at many different kinds of stars. This means we can start mapping out exoplanet occurrence rates as a function of stellar metallicity, stellar age, stellar type, just as some examples of the sorts of things we can now do. So I'll start with one, stellar type. So we could already see from the Kepler data this very interesting result that small planets planets below about 2.5 times the size of the Earth seemed to be more frequent with smaller stars. So F stars, G stars, K stars. This is the occurrence rate of short period small planets, and it's going up. There are more of these planets around smaller stars, which might seem counterintuitive since larger stars have larger protoplanetary disks and therefore more material with which to create planets. So Kepler, again, because it was looking at F, G, and K stars, didn't really look at many M dwarfs. There were only about 3,000. But if you look at those M dwarfs, you can see that this trend continues up to, it seems like M dwarfs are actually very good at making rocky planets in short periods. They seem to be ubiquitous. And then if you take the mid M dwarfs and kind of split them into M3, M4, M5, you can see that this rough trend continues. Even within Ms, this seems to be going up. And I wanted to point out that this is work being done by the postdoc that I work with, Kevin Hardegree-Ullman, who did this work with Kepler and is now using the order of magnitude more M dwarfs observed by K2 to improve this. We'd like to know, are there any features in this? Does it turn over? Does it keep going up? Do you end up with like a rocky planet catastrophe at some point? So he's working on this right now, also on the job market. So look out for his applications. Another thing that K2 observed was many young stars. So here on this plot, what I'm showing is the age of the stars, and there are 4 clusters, 4 young clusters observed by K2. So Upper Scorpius is only 5 to 10 million years old. Then you have the Pleiades at about 100, and the Hyades and Praesepe at about 600 million years. The reason it's interesting to have these young stars is that we have these proposals for mechanisms to create and move planets around. And the different methods that have been proposed to create planets and move them around take different amounts of time. So for instance, forming planets, if your planet is like gravitational instability, just gas accretes a lump of gas fragments, boom, you have a planet, that happens very quickly. If you have planets that grow by collision, core accretion, planetesimals building up, that takes a lot more time. That takes more like 100 million years. And similarly with migration, if you have disk-driven migration, which can only happen by definition while the disk is there, it has to happen very quickly. But if you have migration due to scattering, where the planetesimals and planets are just moving around and dynamically scattering each other, that can take hundreds of millions of years. So what K2 does is let us look at occurrence rates as a function of age and to start constraining which of these processes is the dominant process for sculpting the planets we see today. So if we look at the stars in Upper Scorpius and we already see all of the planets we expect to see based on the Kepler field, and they're already at all the positions we expect to see them based on the Kepler field looked at billion-year-old stars, then we know the processes must be very rapid. So that is why we want to do this. We want to look at exoplanet occurrence rate as a function of age. Okay, so we go back to our 3 ingredients. What are the 3 ingredients we need to do occurrence rates? The first is a uniform stellar catalogue. So this is work that Kevin Hardegree-Ullman, the postdoc, has been doing. He used the combination of Gaia DR2 colors and distances and Lamoste spectra to update parameters, so temperature, surface gravity, metallicity, mass and radius, for nearly 30,000 stars. And then, this was the trick, he used that as a training set to do the rest of the stars looked at by K2 and get good stellar parameters for them as well. So we have this final set here on the right of 185,000 stars that have been had their parameters uniformly derived. And this is compared to when you derive the parameters from the original photometry that we had. And you can see there's a lot of pollution by giants down here on the main sequence. So this has all been cleaned up here. One of the things that having accurate stellar parameters lets you do is get accurate planet parameters. And the very first thing that happened when we did this, when we had accurate stellar parameters for K2, was that this key result from Kepler popped out again. This result is that small planets are bimodally distributed in radius. So if you look at the radii of small planets found with Kepler, there's a peak at super Earth-sized planets and then another peak at sub-Neptune-sized planets. If you look with K2 all across the sky, you see the same distribution. You see these two peaks, super Earths and mini Neptunes. What that means is that this quite unexpected Kepler result is not some quirk of that one patch of sky that we looked at, some weird data thing. It's ubiquitous to the small planet population across the sky, which means it's a fundamental property of small planets. And now there are a bunch of theories to explain why this might happen. So it was exciting to confirm that result with an independent sample. The second ingredient is the Uniform Planet Candidate Catalogue. This is work that John Zink, the graduate student, is doing. Just last month, we finally finished all of the K2 campaigns that were appropriate for this study. Here's our catalogue, 780 planet candidates from K2, including 245 that haven't been published by other groups before. And having this full pipeline that does all of the detection and classification uniformly means that now we're in a position to do this final ingredient, the completeness and reliability tests. And after that, occurrence rates. I'm very excited because I've been working for many years to get the data to this point. So this is really cool. Okay. Now, everything I just said about K2, the ways in which it's better than Kepler for doing occurrence rates, is magnified by another order of magnitude for TESS. So TESS was launched in 2018 and actually smaller than Kepler. It's 10 centimeter cameras, 4 10-centimeter cameras instead of a 1 meter camera, a 1 meter telescope rather. But the way they're laid out, you can get 90 degrees of the sky in one field of view. So TESS is mapping the entire sky with 30-minute cadence. From 1 month at a time, basically. It does this wedge and it moves and does another wedge and it moves and does another wedge. It's predicted to find something like 10 to 16,000 planets, not planet candidates, genuine planets. And a couple thousand of them will be Neptune-sized and below. So that's a lot of planets. That's very cool. As I mentioned earlier, we're at about 4,000 known planets at the moment. So if TESS lives up to its predicted potential, we're going to quintuple the number of known planets with this mission. Now, TESS is not designed to be a statistics mission at all, but it is sampling the whole sky at 30-minute cadence during the prime mission, which was the first 2 years, and then 10-minute cadence in the extended mission, which it just started a couple months ago. The exciting thing about TESS is looking at bright stars. It's only 10-centimeter telescopes, so it's only looking at bright stars. But that means those planets that TESS finds, we can discover much more about them. The Kepler planets are too faint to do a lot with. We did a small patch of sky quite deep, where TESS is doing the whole sky, but quite shallow. So we can't measure the masses of most of the Kepler planets, and we really can't look at the atmospheres of most of the Kepler planets. The planets TESS finds will allow us to do this. And that means we can actually start to ask even more fine-grained questions, like how common are different classes of planets? How common are planets with cloudy atmospheres versus clear atmospheres? How common are things like water worlds compared to rocky planets that are just the same size? And I'm really excited about that because now we're moving on from just radius spins or mass spins, and now we're talking about compositions and types of planets, which is super interesting. And this is just to show the mass of the planets and the radius of the planets. What TESS is going to do is to really map out how this composition, how the mass radius diagram works for small planets, which is clearly still very unconstrained. And this is a plot showing the atmosphere metallicity of planets that TESS will really help fill this out. So this dotted line here is the solar system relationship between the mass of the planet and how many metals it has in it. And for a little while, it looked like exoplanets also followed to this. But then we got more data and it looks like they don't. So we need TESS to kind of work out like how common are planets with different kinds of atmospheres and what are the trends. We do have a TESS demographics working group. So if you are at all interested in TESS exoplanet demographics, let me know. I'm the chair of this working group. You can join our calls and be part of the wider group that's working on demographics. Okay, in the last 10 minutes or so, I want to step all the way back and start looking at this big picture. How do we start piecing together the actual true population of planets? So what I'm showing on this plot is the mass of the planet versus the semi-major axis of the planet. So this is fairly close to what I was showing earlier, which is size and period. I've just mapped them onto different axes. You don't actually get the mass of transiting planets, so I've had to use a mass radius relationship here based on that previous plot that I showed to turn the radii of all the Kepler planets into masses. But here's the distribution of transiting planets. Now there's a bunch of observational biases happening here. This sensitivity drop-off, we don't think it's due to a real drop-off in the number of planets. It's due to the drop-off in Kepler's sensitivity and ground-based transit survey sensitivity. This gap in here, we believe is real because there's no reason why surveys would be able to find these planets, but not these planets. So that's already really interesting. And then you see this drop off as you go to longer, further semi-major axes. And that's because of the geometric probability of transits and the duration of transit surveys. We're just not sensitive to them yet. So those are the transit ones. They're all blocked over there. Short periods. These are the planets that have been discovered by radial velocity, which relies on the Doppler wobble of the star. Radial velocity surveys have actually been going for several decades now, so we're actually sensitive out to like 10 AU planets out here. There are certainly short period things. This, again, this wedge here that's empty is a sensitivity cutoff, not a real drop in the population of planets. So you can see the detection biases again, creating this gap here. These are the microlensing exoplanet discoveries. Just last week, microlensing crossed 100 planets. So hooray for microlensing. What you don't see here is this drop-off in mass that you saw with transit and radial velocity. And that's because microlensing is actually sensitive to the mass ratio between the planet and the star, not the mass of the planet. So actually that gets smeared out here because they're looking at a variety of stellar hosts. And they're sensitive around the snow line. So the snow line is the distance from the star where things like water and carbon dioxide and things start to freeze out and become ice. So microlensing is sensitive to things around the snow line. And finally, these are the direct imaging planets, which are way out here. You have to be very far away from the star in order to be able to block out the light from the star and see the planet. These are also all very young. So it's unclear if you aged this population up to 1 billion years old, whether they'd still A, be here where we see them, and B, be the mass that we measure them at. So for direct imaging, you don't really measure the mass either. You measure a luminosity, and then you use a model to turn that luminosity into a mass. And you have to make some assumptions about how luminosity of young substellar objects changes with time. So you can see, to put all these planets together on the same plot, I've already had to do a bunch of work. And I've had to make a bunch of assumptions about mass radius relations, about stellar hosts, about ages of systems. But there is possibility here. Each of these methods does have some overlap with another method. So transits and radial velocities look at the same stars, same planets. Radial velocity and microlensing look at the same planets. Microlensing and radial velocity and imaging kind of have a little bit of overlap out here. So you might start to imagine building this ladder, this planet demographics ladder, analogous to the cosmological distance ladder, where you measure distance with a bunch of different techniques, but you find the overlap and calibrate them so you can see that they all fit together. But the problem is there's still a lot of work to do. You have to assume a mass radius relation. Which one is right? TESS will help us answer that. You have to assume a mass luminosity relationship. Which one is right? The next generation of exoplanet direct imaging surveys will help us answer that. And better modeling, always better modeling. I don't want to make you think that no work has been done here. So this is work by Christian Clanton and Scott Gowdy from 2016. So they tried to get the microlensing and the direct imaging and some of the radial velocity data together and basically forward model what the underlying population might be. Now, you can see from this color shading here that most of what they found were upper limits or extrapolations. So they weren't working with a lot of data yet. But they did develop a methodology, a framework for saying, here you take your population, you forward model it through the detection sensitivity of your different surveys, and then you come up with an answer for what that original population must have been. One takeaway here is that the highest occurrence rate they extrapolate is here between about 1,000 and 10,000 days, and for the smallest mass, the smallest mass planets. So this is where they find their peak. Recently, there was work, this is a figure from Eric Nielsen's paper from last year, trying to combine the results of radial velocity surveys, which are these two here, Cumming and Fernandez, and imaging surveys. And interestingly, both of them kind of agree with Christian Clanton's result, which is there's some peak, there's some turnover in the occurrence rate of planets between 1 AU and 10 AU. It's a little unclear exactly where that break is, and whether or not it's the same break as this, because these are actually lower mass planets because of the microlensing, and these are giant planets because it's radial velocity at long orbital period. But you can see that people are starting to try and do this, to piece these things together. The last thing I wanted to say about this is that the Roman telescope actually has quite a large grasp of this space. So Roman will do a microlensing survey of the galactic bulge for 500 days and is actually sensitive to planets across a wide range of semi-major axes and a wide range of mass. So Earth is here, kind of, this, I might have drawn this a bit generously, it's kind of at the edge of Roman's sensitivity, which means it might help us with discovering A to Earth, better constraining A to Earth. But Roman may help us calibrate all of these things by covering some of the space of each of the 4 detection techniques. So we have NASA's Exoplanet Program Analysis Group has a science interest group called Exoplanet System Demographics. I'm one of the co-chairs with Michael Meyer, and our goal is to do this, is to bring together experts from the 4 different major detection techniques. Fingers crossed astrometry at some point becomes successful with Gaia, and then we'll include them as well. And we want to do this. We want to put these pieces together. We want to map out the planet mass function and orbital surface density distributions. And we want to, come up with this holistic picture of what the true underlying planet population is. Feel free to join us in our efforts if this is interesting to you at all. I also wanted to advertise. I'm fully into the advertisement part of my talk now. As Yilin mentioned at the start, one of the silver linings of the pandemic has been the ability to attend conferences that one might not normally be able to attend. So we have a conference that I'm the chair of the SOC for called Exoplanet Demographics. Originally was going to be in Pasadena in November, now will be fully virtual. Fully free because it's a NASA conference, no registration, fully virtual. Please come and join us in learning more about the latest state-of-the-art exoplanet demographics result. Here's the website. It's November 12th. It's November 9th to actually 13th now because we've shortened the days. Everybody has Zoom fatigue, right? That's 100% a thing. So we made the days shorter but added an extra day to accommodate that. So registration is still open. Please come join us. So in summary, Kepler is very close, I think, to answering its primary science objective of measuring how common planets like the Earth are. There are still some second-order corrections that we need to measure and make, but I feel confident that the answer is something like 10 to 20 to 30%, somewhere in there, maybe 50%. Of stars like the sun have an Earth-like planet in the habitable zone. And that's pretty amazing to be able to say that. Think of the number of sun-like stars in the galaxy, 10 billion, multiply it by 50%, or even 10%. That's a billion Earth-like planets in our galaxy. 10 years ago, we didn't know what that number was. It could have been 1. So knowing that Earth-like planets are common is super exciting. K2, this is a project I've been leading for a few years, is a very exciting opportunity to extend the analysis of Kepler to new kinds of stars and to really start constraining the physical processes that create planets, turning the stamp collecting into the science. And we have finally finished our planet candidate catalog, which is very exciting. TESS, which is our latest and greatest exoplanet mission, will allow us to start doing occurrence rates for different types of planets. You know, you can really start to bin things up and find out what kinds of planets are the most common, what compositions do they have, what atmospheres do they have. We're still a few years away from that, but it's a very exciting data set that I hope we get a chance to exploit. And finally, there's a lot of opportunity with all of these different surveys that are happening right now. The transit surveys, the next generation of high precision radial velocity surveys are starting to be built and be deployed. The next generation of imaging surveys are being designed and getting up and running. Astrometry may become big with Gaia, fingers crossed. There's a lot of exciting potential there to answer some interesting questions if we can get all of the surveys to talk to each other. And that's the goal of my talk, is to say we should all talk to each other. All right, thank you so much, everyone. Let me know if you have any questions.
Very good. Thank you so much for this talk. I don't know if there are questions from the audience. I can start with a question while people think about things they want to ask. You showed us the distribution of small planets from K2 compared to the one from Kepler.
Mm-hmm.
And from what I saw, the peak of the mini Neptunes in the K2 sample is smaller, is lower than that of the Kepler sample. I was wondering if you can comment on whether you think this is like evolutionary or the samples are.
Yeah, no, that's a really good question. And we looked at that as well, because it seems like both of those peaks are maybe slightly smaller. We don't think it's a real, we think it's in the noise. If you compare these two populations using something like an Anderson-Darling test or a KS test, they're basically the same. You can't really distinguish between them. So we think it's in the noise. But it was suggestive, and we did the same thing. We were like, ooh, what's that?
Because there were some papers this year that actually point out to this comparison about the populations in terms of like ages, right? Whether it's very young or very old. Of course, there's no much more.
Yeah.
There.
So now that we have the full catalog, one goal is to like split the catalog in half by age and say, all right, put all the younger stars in one bin and all the older stars in another bin and make this plot and see, does it look the same? Are they statistically different?
Okay, I look forward to this.
Me too.
There's one question from Rafael, if you want to go ahead.
Yes, thank you very much for your talk. It was excellent. I enjoyed it very much, and I learned a lot.
Thank you.
I have a very elementary question. What about TESS observing M stars? How many M stars can TESS be able to measure? Or M or K, I don't know.
I can actually show you that figure. It's here, in a different PowerPoint that I have open. So here are the distributions of stars observed by Kepler, K2, and TESS as a function of mass. So if I'd had more time, I was planning to include this slide, but I didn't want to overcram it. So this K2 sample here, this is the order of magnitude more that I was talking about, that now we have the ingredients to sample that Kevin will work on. But the opportunity with TESS is even greater. You can see there's actually, many, many thousands of M dwarfs that are observed by TESS that will let us do this, probably in even greater detail. We can really start to cut it down in terms of early M's, mid M's, late M's, old M's, young M's, metal poor M's, metal rich M's. TESS is an incredibly exciting opportunity. But it is a lot of data, and there's no funding to do demographics because it's not a demographics mission. So I will be throwing myself on the mercy of the granting agencies for the next few years to say, let us do this. It's so cool.
Thank you.
No worries.
Okay, I'm going to ask another question because nobody is raising their hands or have put anything in the chat. Feel free to ask questions in the chat. So So I know that one of the primary missions, like one of the primary goals of Kepler was to find this at a Earth, right? And you have shown us like how far this is, that this has come along, and it's so exciting that we're almost there. So my question is regarding to like the calculation of occurrence rate for other populations that are not Earth-like, but could be at shorter periods, which is also where most of the planets from Kepler have been found. How are we doing with those?
That's a really good question. So I concentrated on A to Earth because that was Kepler's main goal. But as Yilin points out, there are most of the planets that Kepler found are at much shorter periods and much larger than Earth. So there's been a lot of interest there. One of the discoveries was that bimodality as a function of the distribution of radii, the super Earths and the sub-Neptunes. That was one of the discoveries. The plot that I showed here today wasn't corrected for things like completeness or reliability. It was the raw K2 occurrence. But for Kepler, it's actually been corrected as a function of the completeness and reliability. So you can actually see these numbers, our occurrence rates as a function of period and radius. Something else that happened was Kepler, short period planets with Kepler gave us the opportunity to measure masses with transit timing variations, which is when multiple planets in the same system tug on each other and interfere with the transit times, so they don't happen exactly regularly. And that led us to down this whole rabbit hole of our radial velocity masses and transit timing masses, are they different? Why are the populations that we're sampling with those two different? And it turns out it was a detection bias, so that was good. There was some tension for a while with the hot Jupiter rate from radial velocities and the hot Jupiter rate from Kepler, but I believe that's been resolved now by careful treatment of the two different stellar samples. So radial velocity looks at a very specific subset of like low stellar activity, slowly rotating G and K stars. Like it's to get good radial velocity, you have to carefully curate your stars. So if you do the same kind of curation with Kepler, I believe that resolves the tension between occurrence rates of giant planets, between radial velocity and transit, which existed for a while. The upshot of the giant planets in short periods is that they seem to be fairly rare. They're in the low single percentage, like 1%, 2% of stars have a hot Jupiter. There's like a whole bunch of other occurrence rates results from Kepler. I can keep going on, but I don't know if that
I just wanted to hear some of them.
Yeah.
Okay, so Luke has a question. I don't know if you want to go ahead, Luke, or if you want to type it in the...
Yes, one thing, I mean, I'm not a specialist in that field, but you had a plot where you have metallicity for the planet's atmosphere around the sun. And I'm surprised to find that Uranus and Neptune has higher metallicity than Jupiter. I don't know where the Earth was on that plot, but could you give us a bit of information? What is it that you're measuring? What do you call metallicity in this case? What's the reference? Thanks.
That's an excellent question. I kind of glossed over this plot because it's also not my specialty, but the gist of it is Jupiter and Saturn are mostly hydrogen and helium, with some solid material in the center, whereas Uranus and Neptune have a lot more of the heavier elements like carbon and nitrogen and stuff. So I believe that when we're talking about metallicity, it's things like carbon and nitrogen as compared to hydrogen and helium. I don't know exactly what is being measured on this plot, but it's a good question.
Thank you.
Okay. Like again for sharing these results with us.
Thank you.
And I can clap for all of us. And thanks for this great talk.
Oh, my pleasure. Have a good day, everyone.